In geometry, transversals are defined as the line that passes through two or more coplanar lines, intersecting them at two distinct points. Suppose we have two lines that lie in the same plane. These lines are equidistant, which means they will not and they will never intersect each other. This would make them parallel. Let us name the red one as line U and the blue one as line V. Let us draw another line, and this time the line passes through the blue and red line, creating two intersection points. This is now our transversal line, or simply a transversal. But wait, you may ask, do transversals intersect parallel lines only? What about other lines? Non-parallel lines. And what if there are more than two lines, say 5 or 6 or even 9 lines, intersected by another line? Is it still a transversal? Let us try to look at these examples. We have here three images. Our first figure, two blue lines are being intersected by a red line. Just by looking at the figure, we can tell that the blue lines are not parallel because they are not equidistant, and they will eventually intersect if the lines extend over the image. Our transversal, which is the red line, does not traverse or cut parallel lines. Instead, in here, it cuts non-parallel lines or lines that meet at a common point. Going to our second image, again, we have two blue lines and the third red line that passes through both lines. We can see that these blue lines are parallel just by looking at the figure, and the third line serves as their transversal. We can conclude in this image that a transversal may or it can intersect parallel lines. Parallel lines can be intersected by any third line, and that particular line will become a transversal. In our third and last example, the lines are not just two, there are more than two lines of the same color. Again, there are three blue lines that are depicted in here, and again, for the third time, a red line passes through all three lines. Obviously, this is again our transversal, but these three lines are shown to be non-parallel, for the first two lines seem to crisscross each other, and the third line will eventually meet both of these lines, given time and more points to be extended from the other two lines. To sum it up, what we can infer from the three given is that our first example shows us that two non-parallel lines can be intersected by a transversal. Our second example shows us that a transversal can also cut through a pair of parallel lines. And for our last example, two or more, in this case, three non-parallel lines can be intersected by a transversal. In conclusion, a transversal may, can, and will do the following depending on the given math problem. Transversals may intersect two or more lines, and these lines, no matter how many there are, may be a set of parallel lines or a set of non-parallel lines. In this math video lesson, let us first study parallel lines and angles formed by a transversal. Now, if lines, parallel or non-parallel they may be, and transversals form two or more intersections or common points, then that would mean consequently that from these points, angles will be formed. 4 angles for each intersection point to be precise. But what kind of angles are they? Let us now study this. We are now back to our two lines, U and V, and then our third line, the transversal line E. We can see that we have our two intersections, our 2 points. Since we only have a pair of lines being intersected in this case, we also only have 2 points given. In our first point, we have our first angle, angle 1, and its corresponding angle, angle 5. For our second pair of corresponding angles, we have the angles 2 and 6. And again, this pair of angles also have equal measures. So we can say that angle 2 is equal to angle 6. For our third pair, we have angles 3 and 7. And since corresponding angles have equal measures, we can also say that angle 3 is equal to angle 7, or the measure of angle 3 is also equal to the measure of angle 7. For our fourth and final pair of angles, we have the angles 4 and 8. Again, and for the last time, this is a pair of corresponding angles. Let us now move on to the next type of angle that is found or formed in a transversal. And these are the vertical angles. Vertical angles are the angles opposite each other when two lines cross. Vertical, in this case, means they share the same vertex or the same origin of point, not the usual meaning of up, down, or vice versa. Again, to illustrate, let us use our two parallel lines U and V and our transversal line T. For our first pair, we have the angle 1 and angle 3. As you can observe, these two angles lie directly opposite or facing each other. If we rotate the line, they may look like an hourglass. For our second pair, we have angles 2 and 4. Vertical angles are also equal in measure, so both of this pair of angles are also equal. We can say that angle 1 is equal to angle 3 and angle 2 is equal to angle 4. For our third pair, we have angles 5 and 7. For our final pair, we have angles 6 and 8. Again, these last two pairs are also equal. Angle 5 is equal to angle 7. Likewise, angle 6 is equal to angle 8. To sum it all up, we now have our 4 pairs of vertical angles. For our next illustration, the third type of angles that are formed or found on a transversal, and these are alternate interior angles. Unlike the first two, these type of angles only include 4 angles, a lesser number of angles compared to corresponding and vertical. Since we are only involving interior angles, the angles not found in the interior are excluded. Hence, we only have 4 angles or half of the usual amount that we can observe on a transversal. For our interior angles, we have angles 3 and angle 5. This pair of angles also are equal in measure. For the second and last pair, we have angle 4 and angle 6. Alternate interior angles are also equal in measure, so we can say that angle 3 is equal to angle 5 and angle 4 is also equal to angle 6. From the two previous illustrations, we can recall that angle 1 and angle 3 are vertical angles, while at the same time, angle 1 and angle 5 are corresponding angles. Since both angle 3 and angle 5 are equal in measure to angle 1, consequently it also means that they themselves are also equal. That is the certain relationship of vertical and corresponding angles. They serve as proof for alternate interior angles. By transitive property, angle 1 serves as the connection between angle 3 and angle 5, proving that they are also equal in measure. Using the same logic and reasoning, the second and final pair angles 4 and 6 are also equal in measure. Since angle 2 and angle 6 are corresponding angles, and while at the same time angles 2 and 4 are vertical angles, we can conclude that angle 2 are equal to both angles 6 and 4, forming a connection and a proof that as alternate interior angles, they are also equal in measure. Again, we have established the connection between vertical angles, corresponding angles, and alternate interior angles. To sum it up, these are our two pairs of alternate interior angles, angle 3 and angle 5, and angle 4 and angle 6. For the fourth and final kind of angles that are found in a transversal, we now have the alternate exterior angles. The same with the interior, we also have 4 angles, excluding the other 4 from the previous illustration. The angles given for the exterior angles are angles 1 and 2 and the angles 7 and 8. But the pairs of angles that are equal in measure are angles 2 and 8. And for the second pair, angles 1 and 7. Again, for each pair, there is a third angle that serves as a connection and proof of their equality. For our first pair, we have angles 2 and 8. From the previous illustrations, we already know that angles 2 and 4 are vertical angles, and while at the same time, angles 4 and 8 are corresponding angles. Because of that, both of our angles 2 and 8 forms a relationship with the angle 4. Thus, by transitive property, we can establish the equality of angles 2 and 8. If they are both equal to angle 4, then they themselves are also equal in measure. For the second pair, we have the angles 1 and 7. The third angle that these angles are both equal to is angle 3. Angles 1 and 3 are vertical angles, while angles 3 and 7 are corresponding angles. By transitive property, because both angles are equal to angle 3, they themselves are also equal in measure. So we can say that angle 1 is equal to angle 7. Now, we have our two pairs of alternate exterior angles. Angle 2 is equal to angle 8, and angle 1 is equal to angle 7. Let us have a quick recap and review all four types of angles that may be formed on a transversal. The first type are the corresponding angles. Of the 8 angles given, there are always 4 pairs of corresponding angles. There are 2 points of intersection in a pair of parallel lines being traversed by a transversal. A particular angle will always have its pair of corresponding angle found on the other point. The second type are vertical angles. For the vertical angles, just like corresponding angles, we have also 4 pairs on each transversal. But unlike corresponding angles, 2 pairs are found already on each point. The third type are alternate interior angles. From the word itself, these are the angles that are found between the 2 parallel lines on each of the intersection points. Unlike the previous 2 types, there are only 2 pairs, excluding the other 4 angles, which consists the last type of angles found in a transversal. These are the alternate exterior angles. If alternate interior angles are found inside or between the parallel lines, exterior angles are found on the outside or the extremes of each point, which are the outermost on each point, the upper and lower angles. All of these types of angles show equality and congruence of measure for each pair given. These are all the 4 types of angles found and formed in a transversal. We will try to answer math problems involving angles on a transversal for our next video. Hope you learned a thing or two and more power to your studies. Thank you and God bless.